Hello friends, welcome to engineering tutorial. So today we are going to resume our discussion on control systems. In the previous videos we discussed about the time domain analysis and time response analysis, some basic questions related to that. So in this video we are going to discuss about another important aspect related to control systems. So in the previous videos related to time response analysis, we discussed some basic questions. So first we'll cover the basic parts, okay, then together we'll be discussing some advanced level questions on that, okay, so don't worry. So in this video we are going to discuss about another important concept related to control systems, which is called as error analysis. So if you remember, when we first started control systems, in the introductory part we discussed that the main objective of the control system is comparison, okay, comparison of values. So the most of the systems where a control system is employed, it has one primary objective, okay. First, the output of the process or whatever system we want to study or we want to evaluate, that obtained output is fed, okay, the output obtained, that is compared with the output which is desired, okay. So this is the actual value, this is the ideal or desired value. So by that a signal, a difference signal is obtained, which is called as error, okay, the error signal. And this error signal is then given to a suitable controller, okay, which is used to produce an actuating signal, which in turn controls the process which provides the output, okay, like this, okay. This, some changes are done so that the output of the process can be altered accordingly so that it matches the desired value. This is the whole point of control systems. So there are two important aspects when it comes to any system. First is accuracy, second is stability, okay. So accuracy is determined with respect to the error analysis, which gives us the error value or how close to the desired value the actual value is, okay. The more closer it is, the better. The less the error signal, the better performing the system is in terms of accuracy. Then is stability. For stability, different types of methods are there. With the help of plots we can find out information about stability of the system, and also there are different criteria, Hurwitz, Routh-Hurwitz, stable, like that. So we'll be discussing that also. So these are the two important aspects. Accuracy gives us information about the performance of the system in terms of its output, how close it is to the desired value. Stability is how long it can do so, okay, without any system breakdown. So these are the two important aspects. So in error analysis, our objective is to find out the error signal for a system, okay. So let us try to understand what it means. Let us say we have a control system, the basic format of a control system like this, GS, input, then we have this. Here deliberately I have taken HS as 1, unity feedback, okay. I have taken unity feedback, this is CS, okay. So the output, this is the input, we can say this is the target value, this is the output, the actual value. So here both of them are compared and this gives us the error signal ES, this. So here I have deliberately taken HS equals to 1. Why? Because only then the value here will be equal to, exactly equal to the value CS. Only when this feedback parameter, the feedback constant will be equal to 1. If it would be any value other than 1, then this value here will not be equal to CS. It will be either lesser than or greater than CS. So in that case comparison cannot happen, because we want to compare RS and CS, okay, the desired value of the input, the target value RS, and the output which is obtained from the system, so that we can get the error signal ES is equal to RS minus CS. The output CS travels through this feedback path and reaches here to this comparator. If the feedback constant HS will not be equal to 1, then this value CS also will not be equal to that exact value. It will either be greater than or lesser than CS. It will not be that value. So for that purpose we have kept this feedback path a constant 1, okay, unity feedback path. So here CS by RS, we know the closed loop transfer function is equal to GS by 1 plus GS. ES, error signal in S domain, is equal to RS minus CS. Here RS minus CS, this is negative feedback, that's why RS minus CS, this ES value. ES is equal to RS minus CS. So here if we take RS as common, then it will be 1 minus CS by RS, okay, we took RS common, then it will be equal to RS into 1 minus CS by RS is equal to, here we have obtained it is GS by 1 plus GS. So that is equal to RS 1 plus GS minus GS by 1 plus GS. So here GS it gets cancelled, so it is simply equal to the error signal ES is equal to RS into 1 by 1 plus GS. This is the error signal. Now the steady state error, okay, the steady state error is given by limit t tends to phi et. It is obtained by final value theorem with respect to Laplace transform, that is equal to limit s tends to 0 s e s. This is the expression of steady state error which is obtained from final value theorem with respect to Laplace transform. Okay, limit t tends to phi et, which is equal to limit s tends to 0 s e s. So that is equal to limit s tends to 0, that is equal to s, here we obtained Es is equal to Rs by 1 plus Gs. This. Okay, this is the expression of steady state error in S domain. This. And here the important part is this input signal, okay, Rs, and the open loop transfer function Gs. These are the two important factors here which contribute to the value of this steady state error. So here we'll be dealing with different types of test input signals. It can be step input, ramp input, parabolic input, and we'll see how this steady state error it responds or it behaves. So there is a method, there are different types of method. So the most popular is the error constant method. Okay, the error constant method we'll discuss. So we'll be discussing about one of the most important methods of error analysis. So it is the error constant method. Okay, error constant method. So we will be dividing our discussion in three main categories. First, it will be the steady state error due to step input. First, this. Okay, so here when the system, okay, it is excited with a step input. Okay, it is excited with a step input. This is AUT. So here we know that the steady state error is equal to, by final values theorem, limit s tends to 0, s Es, which is equal to limit s tends to 0, s into Rs by 1 plus Gs. So here this is the step in signal, RT is equal to AUT. Laplace transform of that is A by S. So we substitute this Rs value here. Then it will be equal to limit s tends to 0, s into 1 by s by 1 plus Gs. Okay, this, then this SS will get cancelled. Okay, it will A by S. Okay, sorry, it is not 1 by S, it is A by S. So this SS will get cancelled and will be only equal to limit s tends to 0, A by 1 plus Gs. Okay, A by 1 plus Gs. So then here limit s tends to 0 Gs, that is equal to a constant which is called as Kp, which is step error constant or position error constant. So this, when we substitute this value here, limit s tends to 0 Gs, this becomes A by 1 plus Kp. Okay, this, when we substitute this value here, limit s tends to 0 Gs here, this becomes equals to A by 1 plus Kp. This is the steady state error. So you understand First, we applied the step input. The expression for steady state error is limit s tends to 0 as Es. Es is equal to Rs by 1 plus Gs. RT is for step input AUT. Laplace transform Rs in S domain is A by S. We substituted it A by S. SS got cancelled, that is equal to A by 1 plus Gs. Limit s tends to 0, A by 1 plus Gs. Now, limit s tends to 0 Gs, which is the open loop transfer function for unity feedback, that is equal to Kp. For step input, that constant value is called as Kp, which is called as the step error constant or position error constant. So we substituted this value here, which is equal to the steady state error for step input, which is equal to A by 1 plus Kp. Okay, so this is the steady state error for step input. Next, we have to discuss the steady state error for ramp input. Okay, suppose the same system is excited by a ramp signal. Okay, this like this. Okay, AT. So here RT is AT, the ramp signal. Laplace transform is equal to A by S square. Okay, so the same thing we'll do. Steady state error is equal to limit s tends to 0 Es, which is equal to limit s tends to 0, sorry, this is SES, okay, S into Rs by 1 plus Gs. Okay, so we'll substitute the value of Rs, that is equal to limit s tends to 0 A by S square by 1 plus Gs. Okay, so here it will be S only. Okay, it will get cancelled, it will be S only. That will be equal to limit s tends to 0 A by S plus SGS. Okay, so here another constant will come into play, that is limit s tends to 0 SGS here for this. Okay, for this. For this part, limit s tends to 0 SGS, and that is equal to Kv, which is velocity error constant or ramp error constant. Okay, this. So here it will be equal to, when limit s tends to 0, this s it will become 0, this s it will become 0. So it will be A by 0 plus this value, limit s tends to 0 SGS, that will be equal to A by 0 plus Kv, or simply A by Kv. That is the steady state error. Okay, ESS due to ramp input is equal to A by Kv, where Kv is equal to limit s tends to 0 SGS. Sorry, here the same thing we did. Okay, here ESS is equal to A by 1 plus Kp, where Kp is equal to limit s tends to 0 Gs. This. Okay, this is for step input, this is for ramp input. Okay, so next we'll discuss the parabolic input. Okay, so now we'll be discussing the steady state error due to parabolic input. Okay, so here the system is excited with parabolic input. So here it is equal to half AT square. In this format, we are deliberately keeping it in this format so that when we'll be taking its Laplace transform, it will be A by S cube. This. Okay, 2 factorial by S cube, 2 will get cancelled in both numerator and denominator and will be simply A by S cube. Okay, this. So again, steady state error, the basic formula is limit S tends to 0 S E S, which is equal to limit S tends to 0 S R S by 1 plus G S. So we'll substitute this value of R S here and it will be limit S tends to 0, okay, here S, it is A by S cube by 1 plus Gs. So here it will get cancelled and become S square. So it will equal to limit S tends to 0 A by S square plus S square Gs. Okay, so here this will become 0 and we are focused or we are concerned with this part in the denominator, S square Gs, or limit S tends to 0 S square Gs. So this will give us another error constant for sorry, for parabolic input, that will be limit S tends to 0 S square Gs, which is equal to parabolic error constant or acceleration error constant. Okay, acceleration error constant or parabolic error constant. Okay, this. So here the steady state error for parabolic input, that is equal to A by K A, this, where Ka is equal to this, limit S tends to 0 S square Gs. Okay, so here in all of these analysis for step input, ramp input and parabolic input, there are some things that you have to be careful about. First is the open loop transfer function Gs. You have to be very clear about it, whether it is feedback with some value or unity feedback system. Then the next thing which you have to do is to determine what type of input is being provided, and depending on that what error constant you have to obtain. If it is step input, then you have to obtain the step error constant or position error constant Kp, which is equal to limit S tends to 0 Gs. This is the step error constant. Then simply put that value here, A by 1 plus Kp. What is this A? Which is the input that is given, the value of the step input. Here it is AUT, or simply RT is equal to A, because it is constant value. RT is equal to A, whatever that value is. So that is for step input. For ramp input, again you have to find out the velocity error constant or ramp error constant, the error constant for ramp signal, which is equal to limit S tends to 0 SGS. Then the steady state error, simply it is A by KV, okay, where A is the value or the factor of the ramp signal, okay, the proportionality constant AT here. So simply put that value in the denominator a by kV. Here it is a by kV. Here it is a by 1 plus kp. So be careful about that. Here it is a by kV only. Okay, where kV is this much. So this gives us this steady state error for ramp signal. Then for parabolic input of the format half AT square, in that case you have to find out the acceleration error constant, okay, or the parabolic error constant, which is equal to limit s tends to 0 s square gs. Then that gives us the acceleration error constant k, and the steady state error is equal to a by k, okay, a by k. So these are the important concepts related to error constant method.